Okay, beginning with example 1, we want to see what happens with distinct linear factors. Okay, so in general, if we're talking very generally speaking, when you are given an integral, you want to try and first say, do I know the answer to this without doing any work? And that sounds a little bit crazy, but it's true for things like cosine theta. If someone throws your way the integral of cosine theta, there's no algebra, there's no calculus really to show. You just know the derivative of sine is cosine, therefore the antiderivative of cosine is sine, plus an arbitrary constant. So do you just know the answer off the top of your head? No. Okay. From there, you want to ask yourself, move up to the next level of sophistication, which would be U sub. Will U sub work? In this example, the answer is no. So then you ask yourself, does integration by parts work? Does it seem viable? Based on what you guys have seen so far in the integration by parts videos, nothing like this has shown up, so let's just say no for now. And then from there, you might ask yourself, well, what about trig sub? Would trig sub work? Trig sub would work here, actually. Trig sub would work. Now, what is going to be easier? Trig sub or partial fractions? Who knows? Well, we'd have to take a look at both, and maybe at the end of this video, I'll do it using trig sub. Okay, but let's just move past trig sub and just think, okay, I have a rational expression, so partial fractions should work. So let's try that. So for partial fractions, first thing you're going to do is let's just forget about the integral. Forget about the integral. Let's just take the actual rational expression itself. Now we know that this factors into two factors. It's a difference of squares. So this is x plus 2, x minus 2. Okay? So now we've got two factors and they are different. So this is the case of distinct linear factors. So for distinct linear factors, for each distinct linear factor, you will create a term of the form an unknown yet to be determined coefficient or constant a over the one factor plus a constant over the other factor. This right here is called the partial fraction decomposition for this rational expression. So this right here is just the decomposition. It's the setup. We don't actually know what the A and B are yet, but that is the basic form. It's the form of the partial fraction decomposition for this rational expression. Okay, a lot of times there are questions where you just want to know what the form is. We don't actually care about finding the A and B. Sometimes it's enough to just talk about that. Okay, so once you have this written out, let's actually kind of forget about this term now, and let's just go directly to that factored form. Okay, and let's get rid of all that. So there we go. We factored it. We removed it from the integral. We're going to put that on hold. And now we are going to clear our fractions by multiplying by the entire denominator of the left-hand side, which will clear the fractions on the left, and then it will cancel the commonalities on the right. So we will be left over with a times x minus 2 and b times x plus 2. All right, now that we are at this stage, there are a couple options for us to figure out what the values of A and B are. So this example 1 video, I'm going to go through the various ways, and not even all of them, but really the ones that are most applicable right now. And then when we move closer to quadratic factors, I'll show you another thing that you can do using complex numbers. I won't do all three methods or whatever each video, just this first one, and then when we get to quadratic, we'll do it there again. So, method one. Method one would be to, these things don't actually have great names. There's no real set names for these methods, so these are just kind of informal made up names. So this, for me, I call this the plug in nice values. So what do I mean by that? Well, you could plug in positive 2. If you plug in x equals 2, then this term here, 2 minus 2, becomes 0, and this whole term just vanishes. So then you'd be left over with 1 equals, well, this here becomes 2 plus 2, so 4 times b. And then you can solve for b by dividing by 4. So that's great. Similarly, another nice value you can plug in is x equals negative 2, and then something similar happens here, and this would be negative 4a. So a equals negative 1/4. So now we have our two needed constants. Now you will notice that they are opposites, same number but opposite in sign. Is that always going to happen? No, but if your factors are of this nice form, then there is a little pattern here. But as you include more and more factors, like down here, then that pattern becomes harder and harder to see. So I wouldn't really think about it as a pattern. At least it's not going to help you really. It's not the amount that you'd have to memorize to know the actual pattern is, I would say, missing the point entirely. So that's one way to get our choice of A and B, is to plug in nice values. Now this method doesn't always work. I mean, it works, but it's not always going to be as quick as just this. We'll see that later on when we have repeated linear factors and irreducible quadratics and things like that. Okay, so that was option 1 for figuring out your constants. Option 2, let's do this up here. Option 2 is going to be, let's see, what do I want to call this? Option 2 would be to equate coefficients. That's what I want to call it. Equate coefficients. Or what other people call it, multiply it all out. So exactly that. What are we going to do? Well, we're going to multiply it all out. So what do I mean by that is, let's take this and let's multiply it all out on the right-hand side. So this becomes 1 equals ax minus 2a plus bx plus 2b. So then I would get my x's together. So I have ax plus bx. So there's my, oops, that's one, the different color there. My x terms plus my constant terms. So 2b minus 2a. So constant terms. All right. So then what you can do, that you have it separated like that, you can go ahead and factor out the x from that one term. So we have a plus b times x plus 2b minus 2a. and I'm just going to put that in parentheses because really I want to emphasize that we have two different terms here. I'm thinking of this as one specific kind of term, and this is another specific kind of term. We've got the x term and the constant term. So now if we look on the right-hand side of this last equation that we have, what we can do here is write the left-hand side also in the format something times x plus something times our constant. So just leaving it as a constant. So I would write this as 0x plus 1 because there's no x's on the left-hand side. Since there's no x's, we would say 0 is the coefficient. So now we can see, lining things up, that there's a correspondence between 0 and a plus b. So must be equal. Because we know that this term doesn't have any x's, we know that these two values must sum to 0. For if they sum to something other than 0, then that would say that there is an x on this side, but there isn't an x on this side, so that would be a contradiction. So these two have to sum to whatever the coefficient of x is on this side. In this case, 0. Now, the constant term on the left must be equal to the constant term on the right. Again, if we have an equation and we know that we've got 14, let's say, is our constant on the right-hand side, and on this side we've got a plus b as our constants, we know that they have to sum to give that constant, or else it wouldn't be a balanced equation and it would be false. So this gives us a plus b equals 0, and it gives us the equation 2b minus 2a equals 1. Solving these equations, we can figure out that a is equal to whatever negative b is, and then we can substitute in the value of negative b for a in this equation. So this would become 2b minus 2, and a is equal to negative b. So this becomes 4b equals 1, which implies that b equals a quarter. And since we know that a is opposite sign of b, we can get that. So clearly this method is great and quick when it is great and quick. There will be some partial fractions decompositions where, depending on if you have repeated roots, then this plug-in of nice values to quickly figure out what your coefficients need to be, they might be quick for some of the coefficients you need, but they might not be quick for some of the other coefficients that you need. So it's really important that you do a blend. You do a blend of these things. This method here might seem lengthy and annoying, but it can be the least of all evils when you're doing a particularly nasty partial fractions decomposition where you've got lots of terms and factors, some of which are repeated, some of which are irreducible quadratic. This at times can be faster once you get the hang of it. Okay, so regardless of which method you choose to do, we find out that a and b are equal to negative and positive 1/4, respectively. Okay, so this actually now tells us the following. We can go ahead and take our generic form for the partial fractions decomposition. And since we know what a is, a was negative 1/4. So, of course, you can put the negative 1/4 like that on top of the fraction as the a was on top of the fraction, but really that's no different than just writing it off to the side. So that's what I'll do. Similarly for b, we know that's positive 1/4, so I'll just put a positive 1/4 in front with a 1 in the numerator. So now, if we integrate this, there's that. Then over here, we can factor those constants out. Oops. Okay. And the nice thing here is these integrals are extremely straightforward. Natural log absolute x plus 2 and natural log absolute x minus 2 plus c. And if you want to factor out the 1/4, and then because we have this log minus this log, remember that we can do the positive coefficient on top and the negative coefficient on the bottom. And there's your antiderivative, written in a nice, concise way. Okay.